Okay, good day. This is Pre-Calculus. I am Mr. McCully, and this is Lesson 48, Introduction to Limits. Let's get right to it. So today we're going to define the concept of limit. We're going to determine if a limit of a function at a given point exists, and we're going to use properties of limits to evaluate limits. So first, let's define that thing. Definition: if a function f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is capital L. The notation for this is this expression right here. And the way that you read it is the limit as x approaches c of the function f of x is L. And I didn't want to do that, but there we go. So what does that actually mean? So let's kind of have a little bit of a thought experiment here. And let's say you driving this green car and your buddy driving this red car decide that you want to meet up at some burger joint somewhere. And so you start driving in along this road this way, and you're driving along this road this way. Both of you hope to eventually end up at the same place, the burger joint. And so the burger joint ends up being, in the context of this problem, the limit. Now, the most important part that you can understand about this is that, again, as I come in from the left, the guy driving the green car wants to get to the same point, and as I come in from the right, the guy driving the red car wants to get to the same point. But what happens if the burger joint catches on fire and isn't there anymore? Well, does that mean that the limit doesn't exist? Well, if I follow along from the left and I follow along from the right, I'm still getting to the same place. So the existence of the burger joint is not necessarily dependent upon the existence of the point that you guys are trying to meet up at. And that is probably the most important and misunderstood concept of limits. Let's review. First off, what does this word arbitrarily close to C mean? And in normal usage, arbitrary use is usually meant to imply something that's random. That's not necessarily the case in this context. In this context, arbitrarily close to C means that it gets so close to C that it's impossible to tell the difference from it being C, yet still not being C. So we're so close you can't tell the difference, but it's still not exactly C. The existence of the limit is dependent on the function going to the same value from both sides of the function. And I have an example where it doesn't go to the same value, and therefore the limit will not exist. And finally, the most important part, the existence of the limit at a value of x is not dependent upon the existence of the point at the value of x. And so a real quick demonstration. Let's say I have a simple graph here, and I'm drawing a graph like this. And here is my C, and here is my L, and I have a hole in that spot right there. And we've talked about holes earlier on in the year. If I say, what is the limit as x goes to C of f of x, being this f of x here, I can have that hole, but because as I go from the left-hand side and as I come in from the right-hand side, the function tends to go towards this L, I can say that this function has the limit L. And that is very important. All right, so some basic limit rules in all cases. B and C are real numbers, and n is a positive integer. So remember, B and C, real numbers. Any decimal, any number that doesn't have I in it is a real number, and a positive integer is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. And so some basic limit rules. If you say what is the limit as x goes to c of some constant b, you'll get b. If you say what is the limit as x goes to c of x, it will become c. And what is the limit of x to the n? As x goes to c, it's c to the n. And then what is the limit as x goes to c of the nth root of x? It is the nth root of c. These are all instances. These are all instances of direct substitution for evaluating limits. This method works for finding the limit of most functions that are continuous for all real numbers. And so what we can do is we can use these basic rules to build up some more or some larger rules. So some quick examples to illustrate these limits or these rules. The first rule, this constant rule here, is expressed in this example where I say, what is the limit as x goes to 2 of 4? Well, 4 is just a constant. And so if I grab my graphing calculator and I graph the function, let's clear this out and let's clear this out. If I graph the function 4, we know that on a standard window, we get this horizontal line. And so here is 2. And what does the function point to as I come in from the left and as I come in from the right? It clearly points to 4. So that limit is 4. What is the limit as x goes to 3 of x squared? Well, we have a property for that as well, and that's this one right here. If it is x to a integer power, we can just plug in that value that we're going towards. And so in this case, we're going to 3, so this is going to be 3 squared, which we can evaluate to be 9. And the limit as x goes to pi over 2 of sine x, well, that kind of goes back to this statement here. The method of direct substitution works for finding the limit of most functions that are continuous for all real numbers. The sine curve is continuous for all real numbers. If you remember way back when, the sine curve looks like this. There are no holes, there are no gaps. So as we go to pi over 2, we can do a direct substitution for just sine x. And the sine of pi over 2, if you remember your unit circle, that's going to be just 1. So those are our solutions for some simple limits. Additionally, some additional properties of limits that can be used based on this. And again, in each instance, b and c are real numbers and n is a positive integer. Additionally, f of x and g of x are functions with the following properties. If you take the limit of f of x as x goes to c, you'll get L. And if you take the limit of g of x as x goes to c, you'll get K. And so if I take the limit as x goes to c of our function f of x times some constant multiplier, it'll just be that limit times the constant multiplier. If you take the limit as x goes to c of the sum or difference of two functions, it'll just be the sum or difference of the two limits. If you take the limit as x goes to the c of the product of two functions, it will be the product of the limits. If you take the quotient of two functions and the limit as x goes to c of the quotient of those two functions, it will be the quotient of those two limits, provided that g of x is not equal to c or equal to 0 when x equals c. So as long as this isn't 0 when you go to c, you can just do that plug-in. And then finally, the limit as x goes to c of some function raised to a power that is a positive what do I call it, a positive integer, will go to the limit as raised to that positive integer. And so some conclusions for that: if p is a polynomial function, and we've done a lot of polynomial functions this year, linear functions, quadratic functions, those are all examples of polynomial functions, and c is a real number, then you can use direct substitution to evaluate that polynomial function to get the limit. Additionally, if q is also a polynomial function and then the rational function r of x is the quotient of p over q, then the limit of that rational function can be solved through direct substitution also, provided that denominator function is not equal to 0 when x equals to z, because then you'd have a division by 0. So let's take a look at a couple examples here. Evaluate the following limits. Use the properties, if possible, of a graphing calculator. So first off, this is a polynomial function. So just as a quick note, this is a polynomial function. And so we can solve with direct substitution. And so this is just going to be 2 times 2 squared, because we're going to 2, plus 4 times 2 minus 6. So I get 4, 8, and then another 8. 8 and 8 is 16, minus 6 is going to give me 10. And so our second example right here, we have the limit as x goes to 3 of 3x over x plus 4. Now this function right here is a rational function, but clearly, as x goes to 3, if I plug in 3, I don't get a division by 0. So we can say, note, since this is a rational function, that is defined at x equals 3, it can be solved with direct substitution. And so if I plug in 3, 3 times 3 over 3 plus 4, that'll give me 9 over 7. And that is the limit. All right, let's take a look at this one. Now, here we have a problem where we have another rational function. But when I plug in 2, I get 2 minus 2 on the bottom, I get 0. So note, this rational function at x equals 2. So we don't have a method. But again, that does not mean that the limit doesn't exist. So if I go to my graphing calculator and I hit my y equals, and I clear out what I had before, and I go alpha y equals, we'll put a fraction there, and we'll go x squared minus 4 over x minus 2. And we hit graph. We notice that there doesn't look to be any kind of a break here. Now clearly, if I bring up my table and I type in 2, let's go down here, go 1 and then 2, I get an error. So clearly there is a division by 0, and clearly at x equals 2, I have a little bit of a hole. But if I think about it in the context of a limit, as I come in from the left and as I come in from the right, this thing looks as if it's going to go towards 1, 2, 3, 4. And so at 2, I get 4. And that turns out to be the limit. And we will have a better explanation why that is true in the next lesson. You get 4. And finally, the limit as x goes to 0 of x over x, we get, note, this is an indeterminate, indeterminate, indeterminate form when x equals 0. So I get 0 over 0, and that's nonsense in the context of real numbers. But again, if I look at the graph of this thing, if I go to my y equals, I delete all of this stuff, and we go math, go over to number, hit 1 for absolute value, Oh, cleared everything out. That stinks. So let's go alpha, y equals, let's go fraction, let's go math, let's go over to number. 1 for absolute value, we want an x on top and we want an x on the bottom. And so I hit graph, and as I come in from the left-hand side, it looks like it's going to -1. And as I come in from the right-hand side, it looks as if it's going to +1. Since the left-hand side and the right-hand side don't point to the same value like they did in the last one, we're going to say that this limit does not exist. All right, well, that's all I got for today, folks. So the Star Wars fun fact of the day, Star Wars The Clone Wars, is rendered in anamorphic 2.4 to 1 ratio, which is usually reserved for big budget cinematic movies like Marvel movies. But it is a crop to the 6:19 ratio that most HD TVs have, so that it fills the screen and little kids don't have black bars above and below their favorite animated characters. That's all I got. So have a good day. Bye.